Welcome! Today, we'll explore LeetCode problem number 1687, delivering boxes from storage to ports. This problem challenges us to optimize trips while balancing constraints on weight and the number of boxes. We'll break it down step by step and discuss efficient approaches. Let's dive in. In this problem, you are tasked with delivering boxes from a storage area to various ports. Each box is represented as a triplet: ports_i, weight_i, count_i. Here, ports_i indicates the port number the box needs to be delivered to, weight_i is the weight of the box, and count_i tells us how many identical boxes are included in this entry. Additionally, there are three constraints to consider. First, ports count specifies the total number of ports available. Second, max boxes is the maximum number of boxes that can be loaded onto the ship in a single trip. Lastly, max weight is the maximum weight capacity that the ship can handle at one time. The ship begins its journey at port 0 and travels in a straight line, stopping at each port to load or unload boxes. The ultimate goal is to determine the minimum number of trips required to deliver all the boxes to their respective ports efficiently. Now, focusing on the output requirements, the solution should return an integer representing the minimum number of trips needed to deliver all the boxes. To clarify this further, let's examine an example. Suppose the boxes list is 1, 1, 1, 2, 2, 1, 3, 3, 1. Here, there are 3 ports, and the maximum number of boxes the ship can carry in one trip is 2, while the maximum weight capacity is 3. The output for this input is 4, which means it takes 4 trips to deliver all the boxes. This result is derived based on the constraints and the sequence of loading and unloading operations at the ports. For the first example, let's break down the trips. In trip 1, the ship loads boxes 1, 1, 1, and 2, 2, 1, delivering them to ports 1 and 2. The ship then returns to port 0 to reload. In trip 2, the ship loads the remaining box 3, 3, 1, and delivers it to port 3. Altogether, this results in 4 trips, 2 trips for deliveries and 2 trips returning to port 0. For another example, consider boxes equals 1, 1, 2, 2, 2, 2, where ports count equals 2, max boxes equals 3, and max weight equals 4. The output here is 3, meaning 3 trips are needed for delivery. Here's the breakdown for the second example. In trip 1, the ship loads the 2 identical boxes, 1, 1, 2, and delivers them to port 1. Then, it returns to port 0 to reload. In trip 2, it loads the 2 identical boxes, 2, 2, 2, and delivers them to port 2. This results in 3 trips, 2 trips for deliveries and 1 return trip to port 0. Finally, let's consider the constraints. The problem can involve up to 10⁵ boxes or ports, and the weight in box limits can reach very high values, so the solution must be efficient. Edge cases include situations where constraints like max boxes or max weight are very restrictive, forcing multiple trips for even a single box. On the other hand, if all boxes are destined for the same port, fewer trips are needed. Varying weights and counts across boxes also require careful planning to optimize the trips effectively. To tackle problem number 1687, we need to minimize the number of trips required to deliver boxes while adhering to constraints on weight and the number of boxes per trip. Several approaches were considered to solve this. First, there's the brute force approach, which involves calculating all possible ways to group boxes into trips and simulating the delivery process for each configuration. While this method is conceptually straightforward, its complexity is exponential. For n boxes, it tests all subsets, leading to O(2 to the power of n) time complexity. This makes it computationally infeasible for larger inputs, especially since n can go up to 10 cubed. On the other hand, a more refined strategy involves using dynamic programming. Here, we define dp I as the minimum number of trips needed to deliver the first I boxes. By evaluating all valid groupings of boxes that end at index I, we can update dp I based on the trips required. A key observation for this approach is that the cost of delivering a group depends on the number of unique ports visited, which can be calculated dynamically during the iteration process. Additionally, the constraints on weight and box count allow us to prune invalid groupings, significantly reducing unnecessary calculations. The dynamic programming steps involve using a sliding window to represent the current group of boxes in a trip. For each box, we check if adding it would exceed the weight or box count limit. If valid, we calculate the number of port visits for that grouping and update DP accordingly. The goal is to minimize DP, by leveraging the previous state. This approach has a time complexity of n squared, due to the nested iterations required to evaluate valid trips, but pruning helps make it manageable for inputs where n is less than or equal to 10 cubed. To address the inefficiencies of this method, we can further optimize it by incorporating a sliding window directly into the dynamic programming process. By doing this, we avoid recalculating port visits and weight checks repeatedly, instead maintaining a running total for the current window. This improvement introduces the sliding window with dynamic programming approach. With the sliding window approach, we define DP, in the same way as before, representing the minimum number of trips for the first I boxes. However, instead of recalculating values for each grouping, we incrementally update the running totals for weight, box count, and port visits as the window expands or contracts. This allows us to process each box only once, significantly reducing the computation time. The minimization of DP, is achieved directly through these incremental updates, and the sliding window ensures that all constraints are respected. The result is a time complexity of n, making this the most efficient solution for the problem. While this approach requires careful implementation to handle edge cases, such as properly tracking the last port visited, it aligns naturally with the problem's constraints and scales well for large input sizes. This balance of efficiency and practicality is why we chose this optimized sliding window with dynamic programming approach as the final solution. The key insight that unlocked this efficient approach was realizing that port visits could be computed incrementally within a sliding window. This eliminated redundant calculations and allowed us to focus on optimizing the dynamic programming transitions. By processing each box only once, the sliding window method reduced the overall time complexity from n squared to n. Among the alternatives, brute force was clearly infeasible due to its exponential time complexity. The basic dynamic programming approach, while an improvement, was still too slow for larger inputs. Combining the strengths of DP and sliding windows, the chosen approach offers both efficiency and elegance. Of course, it does require extra space for the DP array and bookkeeping variables, but this trade-off is negligible compared to the computational savings. While implementing the sliding window approach is more complex than the brute force method, the significant performance gains make it the optimal choice for solving this problem effectively. The problem delivering boxes from storage to ports involves managing the delivery of boxes with specific constraints while minimizing the total number of trips. Each box has a designated port it must be delivered to, along with a specific weight. The constraints limit the number of boxes that can be carried in one trip, which is capped by max boxes, and the total weight of the boxes, which must not exceed max weight. Additionally, after delivering boxes to different ports, the truck must return to the storage before starting the next trip. The goal is to find the optimal way to minimize these trips while adhering to these constraints. To solve this, we first need to interpret the input and constraints accurately. The input consists of a list of boxes, each represented as an array, port, weight, and the parameters max boxes and max weight. The output should be the minimum number of trips required to deliver all the boxes while following the given rules. Key observations are essential to constructing an efficient solution. First, delivering boxes to the same port consecutively can help avoid unnecessary trips, as grouping deliveries reduces the number of port visits. Second, the truck must always return to storage after completing a trip, so we must account for these return trips in our calculations. Optimizing the solution involves balancing the constraints of max boxes and max weight while minimizing the number of port visits. To achieve this, we employ a two-pointer sliding window approach to represent the boxes being delivered in a single trip. This allows us to dynamically adjust the range of boxes considered for delivery. Additionally, dynamic programming is used to efficiently compute the minimum number of trips required. The key data structures include a DP array, where DP, stores the minimum trips needed to deliver the first I boxes, and sliding window variables to track the current window of boxes, their total weight, count, and the number of unique port visits. To initialize the dynamic programming solution, we set DP 0 equals 0, as no trips are needed when there are no boxes to deliver. For all other indices, we initialize dp I equals infinity, which will later be updated dynamically as we compute the minimum cost for delivering the first I boxes. Next, we set up the sliding window using two pointers, start and end, to represent the range of boxes being considered for delivery on a single trip. The sliding window must satisfy two key constraints: the total weight of the boxes in the window must not exceed max weight, and the total number of boxes must not exceed max boxes. As we iterate through the boxes, we expand the window by incrementing the end pointer to include more boxes, ensuring that these constraints are maintained. Simultaneously, we track the number of unique port visits in the current window, which is critical for calculating the cost of the trip. If at any point the window violates the constraints, we contract it by incrementing the start pointer until the constraints are satisfied again. To calculate the cost for the current window of boxes, we consider two components: the number of unique port visits within the window and the mandatory return trip to storage after delivering the boxes. The total cost of delivering the boxes in the current window is the sum of these two values. We then update the dynamic programming array dp end as follows: dp end equals min dp end dp start plus visits underscore in underscore window plus 1. This ensures that dp end always holds the minimum number of trips required to deliver the first end boxes. We repeat this process for all boxes, continually expanding and contracting the window as necessary to satisfy the constraints and dynamically updating the dp array. At the end of this iterative process, the dp array will contain the minimum trips required for any number of boxes, and the result for the entire problem will be stored in dp n, where n is the total number of boxes to deliver. The efficiency of the solution lies in its ability to avoid redundant calculations. By using a sliding window, we ensure that each box is processed only once, leading to a time complexity of O(n) for the main loop. This is because the window expands and contracts dynamically without revisiting boxes unnecessarily. Minimizing the number of port visits is another critical aspect of the solution. By grouping boxes destined for the same port together, we can reduce the number of unique port visits, which directly impacts the trip count. The dynamic programming transitions are also highly efficient. By leveraging the pre-computed values in dp start, we can calculate the cost of the current window without recomputing previous states. For complexity analysis, the time complexity is O(n), with an additional O(k) overhead for calculating port visits in the worst case, where k is the number of ports. The space complexity is O(n) for the dp array, with an additional O(1) for sliding window variables, making this approach both time and space efficient. Here, we begin by importing the deque class from the collections module, which will help us efficiently manage our sliding window operations. Then, we define the solution class and its method boxDelivering, which takes in the list of boxes, the total number of ports, and the constraints on the maximum number of boxes and their total weight. We initialize several variables to facilitate our dynamic programming solution. The dp array keeps track of the minimum number of trips required to deliver boxes up to each point. The trips deque will be used to maintain a monotonic queue of potential solutions. The variable j represents the start of the current window, current weight tracks the total weight of boxes in the current window, and port visits counts the number of distinct port visits for the window. Now, the core of the logic begins with a loop that iterates over each box. At the start of the loop, we add the weight of the current box to current weight. If this box's port differs from the previous box's port, we increment the port visits counter. Next, we ensure that the sliding window respects the constraints of maximum boxes in total weight by adjusting the start of the window, j. If the window becomes invalid, we subtract the weight of the box at index j from current weight and adjust port visits if necessary. Finally, we increment j to shrink the window. Within the loop, we also prune the trips deque to ensure it only contains elements relevant to the valid window range. Once the sliding window is adjusted, we calculate the cost of making trips for the current window. This cost is the value at dp j, representing the minimum trips to deliver boxes up to the start of the window, plus the number of port visits in the window, and an additional 2 trips for picking up and delivering the boxes. To maintain the efficiency of our solution, we use a monotonic queue to keep track of the minimum costs. If the cost of the current solution is less than or equal to the last element in the trips deque, we remove the less optimal solutions from the deque. We then append the current box index and its associated cost to the trips deque. After updating the DEEC, the minimum cost for delivering boxes up to the current point is stored in DP, I, which is derived from the front of the trips DEEC. Finally, after processing all boxes, the result is stored in DP, N, which represents the minimum trips needed to deliver all boxes, and we return this value as the final result. Here, we start by defining the main method box delivering that takes the array of boxes, the number of ports, the maximum number of boxes allowed per trip, and the maximum weight that can be carried. We initialize the length of the boxes array as n and create a dynamic programming array DP to store the minimum cost for delivering boxes up to a certain index. Additionally, we use a DEEC named trips to manage the state of the sliding window efficiently. The variables j, current weight, and port visits are initialized to help track the start of the sliding window, the total weight of boxes in the current window, and the number of port visits needed, respectively. Inside the loop, we iterate through each box, adding its weight to current weight. If the port of the current box is different from the previous one, we increment port visits since delivering to a new port incurs an additional cost. Then, to ensure we adhere to the constraints of max boxes and max weight, we slide the window by adjusting the starting index j. As we remove boxes from the window, we update current weight and decrement port visits if removing a box changes the port sequence. This setup helps us maintain a valid sliding window while preparing for the next step of the algorithm. Next, we handle outdated elements in the DEEC. Since the sliding window's start index j has moved, we remove entries from the front of the DEEC that are no longer valid. This ensures our DEEC only contains relevant states. Then, we calculate the cost of trips for the current window as dp, j, plus port visits plus 2. The plus 2 accounts for the cost of traveling to and from the ports during one trip. To optimize the dynamic programming solution, we maintain a monotonic queue. We remove elements from the back of the DEEC if their cost is greater than or equal to the current trip's cost. This ensures the DEEC always contains the smallest DP values for efficient lookups. Afterward, we add the current index and its cost to the DEEC. Finally, the DP value for the current index is updated using the minimum cost from the front of the DEEC. Once the loop completes, the answer is stored in DP, N, representing the minimum cost to deliver all the boxes. This approach efficiently balances the constraints while minimizing the delivery cost. To begin solving this problem, we initialize an array DP where each index represents the minimum trips required to deliver boxes up to that point. Initially, DP equals 0, 0, 0, 0, since no trips have been made yet. We also set up a DEEC trips to store the cost of trips dynamically, a pointer j to manage the sliding window, and variables current weight and port visits to track the window's weight and the number of unique port visits. Starting with I equals 1, we add the first box, 1, 1, to the window. The weight increases to 1, and since there is no port change, port visits remains at 0. Calculating the cost for this trip gives dp, 0, plus port visits plus 2 equals 2, so we update the DEEC to DEEC, 1, 2, and set dp, 1, equals 2. Moving to I equals 2, we add the second box, 2, 1, which increases the weight to 2. This triggers a port change, so port visits becomes 1. At this stage, we calculate the cost as dp, 0, plus port visits plus 2 equals 3 and update trips to DEEC, 2, 3, with dp, 2, equals 3. Continuing with I equals 3, we add the third box, 1, 1, which brings the total weight to 3. Here, another port change is detected, so the port visits count increases to 2. Calculating the cost for this trip results in dp, 0, plus port visits plus 2 equals 4. We update the DEEC to DEEC, 3, 4, and set dp, 3, equals 4. At this point, we've processed all boxes for the first example, and the minimum number of trips required is stored in dp, 3, which is 4. This demonstrates the process of dynamically calculating trips while adhering to the constraints of max boxes and max weight. Now, transitioning to a second example with larger constraints, we observe a new setup with 6 boxes, 3 ports, and more relaxed limits for max boxes and max weight. Here, we initialize dp as 0, 0, 0, 0, 0, 0, 0 to accommodate the 6 boxes, and reset trips, j, current weight, and port visits to their initial values. For I equals 1, adding the first box, 1, 3, increases the weight to 3 with no port change. The trip cost is calculated as dp, 0, plus port visits plus 2 equals 2. We update the deek to deek 1, 2, and set dp 1 equals 2. For I equals 2, adding the second box, 2, 2, brings the weight to 5, and a port change occurs, setting port visits equals 1. The cost is calculated as dp, 0, plus port visits plus 2 equals 3, so trips becomes deek, 2, 3, and dp, 2, equals 3. For I equals 3, we add the third box, 3, 1, reaching the maximum weight of 6. With another port change, port visits becomes 2, and the cost is dp, 0, plus port visits plus 2 equals 4. Updating trips to deek, 3, 4, we set dp, 3, equals 4. At I equals 4, we slide the window to maintain constraints. Removing box 1, 3 reduces the weight to 3 and decreases port visits to 1. Adding the next box 3, 1 raises the weight to 4, and the cost becomes dp 1 plus port visits plus 2 equals 5. We update trips to deek 4, 5 and set dp 4 equals 5. After processing all boxes in this second example, we observe that the minimum number of trips needed is stored in dp 6, which equals 5. This reflects how the algorithm adjusts dynamically to handle larger constraints while adhering to the rules for weight and box limits. Now, let's examine a more constrained edge case with just one port, a smaller max boxes limit of 2, and a max weight of 6. This example will demonstrate how the sliding window approach efficiently manages tight constraints. Starting with dp equals 0, 0, 0, 0, 0, and the same initial variables, we examine the first two boxes, both 1, 3. For I equals 1, adding the first box sets current weight equals 3 and the cost to 2. We update the deek to deek 1, 2. For I equals 2, adding the second box reaches the weight limit of 6, and the cost remains 2. Because we cannot exceed the max box's limit of 2, the window size is maintained by keeping j equals 0. As we progress to I equals 3, the constraints require sliding the window. Removing the first box, 1, 3, brings the weight back to 3 while maintaining the port visit count. This allows us to add the next box, 1, 3, without exceeding the limits. Following this process, the algorithm ensures that we respect the constraints while minimizing the number of trips. By the end of this edge case, the final state of dp-1 reflects the minimum trips needed to deliver all boxes. This example highlights the efficiency of the sliding window approach combined with dynamic programming, showing how the problem is solved optimally under varying constraints. The time complexity of this solution is primarily determined by analyzing the sliding window mechanism and the operations performed within the loop. First, we have the outer loop that processes each box. Since the loop runs from I equals 1 to I equals n, where n is the total number of boxes, it iterates exactly n times. Next, we have the sliding window adjustments managed by the j pointer. This pointer ensures the constraints on max boxes and max weight are respected. Importantly, the j pointer only moves forward, and since each box is processed exactly once when j increments, the total number of iterations for this while loop across the entire algorithm is also n. Lastly, there's the monotonic queue, trips, which efficiently tracks trip costs. Adding or removing elements from this queue is an amortized O1 operation, and since each box index is added and removed at most once, all queue operations across the entire algorithm sum to O(n). Together, these components contribute to an overall time complexity of O(n). In addition to the previous operations, we also consider the cost calculation step. This involves expressions like cost equals dp, j, plus port visits plus 2 and array updates such as dp, I, equals trips, 0, 1. These are constant time operations, O(1), and since they occur once per iteration of the outer loop, they contribute O(n) overall. Combining everything analyzed so far, the outer loop, sliding window adjustments, monotonic queue operations, and cost calculations, the final time complexity remains O(n). Now, let's analyze the space complexity. The dp array, used for dynamic programming, has a size of n plus 1, where n is the number of boxes. This contributes O(n) space. The monotonic queue, trips, stores indices and costs to maintain the monotonic property. In the worst case, it can hold all n indices, so it also requires O(n) space. These two components are the primary contributors to the overall space complexity. In addition to the dp array and trips deek, we consider the space used by variables such as current wait, port visits, j, and cost. These are simple scalar variables and require only constant space, or O1. When we combine all space considerations, the DP array, trips dq, and a few variables, the overall space complexity of the solution is O(n). Now, let's evaluate the algorithm across different scenarios. For the best case, the algorithm processes each box exactly once, leading to a time complexity of O(n). In the average case, even with typical input distributions, the sliding window adjustments and monotonic queue operations remain efficient, ensuring O(n) as well. Finally, in the worst case, where constraints like maxboxes and maxweight require frequent updates, the algorithm still processes each box at most once, maintaining its O(n) complexity. This consistent performance across all scenarios highlights the efficiency of the approach. To appreciate the efficiency of this solution, let's compare it with a brute force approach. A naive method would involve checking the cost for every possible subarray of boxes. This would require O(n²) iterations for the outer and inner loops. Additionally, recalculating port visits and waits for each subarray would add even more computational overhead. In contrast, the optimized solution leverages a sliding window and monotonic queue to handle constraints efficiently and minimize redundant calculations. These techniques reduce the time complexity from O(n² to O(n). Mathematically, we can prove this by noting that the sliding window ensures each box is added to and removed from the window at most once, contributing O(n). Similarly, operations on the monotonic queue are amortized O(1) per box, resulting in O(n) overall. Updates to the dynamic programming array also occur in O(n). Altogether, the total time complexity is O(n), while the memory usage remains O(n) due to the DP array and the monotonic queue. When tackling this problem, there are a few common mistakes to be aware of. First, it's easy to misunderstand the problem constraints. Many people fail to account for both the weight limit and the box capacity constraints at the same time. If you ignore one of these, it can lead to incorrect calculations for the number of trips required. The best way to avoid this is by carefully parsing the problem statement and making sure you clearly identify all the constraints, like the maximum weight W and maximum box limit K. Another frequent issue is overcomplicating the solution. Some may attempt to simulate all possible combinations of trips, which often results in exponential time complexity. Instead, focus on efficient techniques like dynamic programming or a sliding window approach, which can help you solve the problem in O(n) or O(n log n) time. Lastly, many struggle with minimizing the number of unique port visits. Simply optimizing for weight or capacity constraints won't suffice. To address this, you can use a two-pointer approach or define a dynamic programming state that explicitly incorporates port visits as part of your cost calculation. Now, another common pitfall is not handling edge cases properly. For instance, consider scenarios where all the boxes are destined for the same port, or where the weight of a single box exceeds the maximum weight limit. These edge cases can easily trip you up unless you write detailed test cases to account for them. Additionally, inefficient state transitions in dynamic programming are a common source of time limit exceeded errors. For example, iterating over all possible previous states can significantly slow down your solution. Instead, you can leverage techniques like prefix sums or monotonic data structures to optimize these transitions. From an interview perspective, it's important to recognize that this is a classic optimization problem requiring you to balance multiple constraints. You should focus on minimizing the number of trips while adhering to both weight and capacity limits. Sliding window and dynamic programming are the two most common approaches here, and understanding when and how to use each is critical. When discussing your solution, clearly explain how you're optimizing for port visits and constraints simultaneously. This shows structured problem solving and clear thinking. You might also want to highlight the trade-offs between the sliding window approach, which is faster but more complex, and dynamic programming, which is easier to understand but potentially slower. This problem shares similarities with several related problems, which can help build your intuition. For example, LeetCode 1091, shortest path in binary matrix, uses BFS to minimize steps under constraints, which is applicable when thinking about minimizing trips or port visits. LeetCode 188, best time to buy and sell stock for, involves dynamic programming principles with constraints, making it a good parallel for managing the multiple limitations in this problem. LeetCode 863, all nodes distance k in binary tree, focuses on distance-based optimization, which can be helpful when considering how to minimize the number of unique port visits. Lastly, LeetCode 146, LRU cache, provides insight into sliding window techniques and memory-efficient solutions, which align well with the approaches needed for this problem. Finally, let's consider some alternative approaches and their trade-offs. The sliding window approach is highly efficient, with a time complexity of O(n), making it optimal for minimizing runtime. However, it requires careful implementation to ensure all constraints are handled correctly. On the other hand, dynamic programming is often easier to understand and implement, especially for problems with multiple constraints. The downside is that it may lead to higher time or space complexity if the state transitions are not optimized. Another option is the greedy approach, which can be intuitive for smaller cases. Unfortunately, this method often fails to handle multiple constraints effectively, making it less reliable for comprehensive solutions. When choosing an approach, it's essential to weigh these pros and cons based on the problem's specific requirements and constraints. Great job! We've covered LeetCode problem number 1687, reviewed the dynamic programming-based solution, and discussed key takeaways. Keep practicing optimization problems, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!